All right, in Chapter 8, Section 1, we have some idea of the central limit theorem that's going on. They talked about in Section 1. So when we have a mean of 84 and a standard deviation of 8, that's what we're used to. But now we're taking a sample size of 64 out of this population. And so what do we think that the mean of the sample means would be? Well, hopefully those means is going to be 84, right? If the population means 84, if we take a mean of all of our sample means that we get, we would hope that it's 84 too. Now our standard deviation is going to be different. So the standard error of the mean, there's a formula, it's the population standard deviation divided by the square root of your sample size. So in our case, we're dealing with 8 divided by the square root of 64. So that would give us a 1. And how I want to look at this is if we are saying, do you know one person, one female that's given birth a month early? And most of us would probably say yes, that we do know that. That's not very strange to have someone that gives birth a month early. Let's say we did a sample of 30 people though, and we found out the mean gestation period was a month early. We would be checking water sources, wondering if our biological gestation process is changing. That would give everyone up into arms. Is this neighborhood over electrical outline or electrical lines? And so if it's just one person, it doesn't seem that rare. If it's a group of people, that seems rarer. So that's kind of what we're looking at with the central limit theorem. If we take a larger sample, we should get closer to the mean, so our amount of variation is less. So here's a problem where we have a population mean and standard deviation, but we're dealing with the sample size of 81. So there's some different parts of the question. Choose a correct description of the shape of the sampling distribution of X bar. We have a pretty large sample size. And so since we have this large sample size of 81, we could go ahead and say that the distribution of our means should be approximately normal. In the book it should say if your sampling size is greater than 30. Now we're doing all these different probabilities, and they're done exactly how we've done before, except we have to calculate a new standard deviation, the standard error of the mean. So still going to go to our normal calculator. So we are going to put our mean in just like we did before. So a mean of 78, standard deviation of 36, and a sample size of 81. Already forgotten it. 78 is our mean. So our mean's going to stay the same. Our standard deviation, since I'm dealing with the sample size, is going to be different. So I'm going to take 36, my population standard deviation, and divide it by the square root of my sample size. And so my standard error of the mean is going to be 4. And so now I can do all the calculations that I'm needing to do. The first one is that the means are greater than 85.8. So just like before, we do a greater than 85.8. And we just plug in the information. But we have to make sure that we get this new standard error of the mean put in for the standard deviation. So 0.0256, just for verification. Wow. The mean was the same. That was for 0.0256. Okay, I think I still remembered it. 0.0256. Right? And then, so on the next one, we'll just do less than 69. And then on part D, we would do a between with those values. So we just have to make sure that we're dealing with that changed standard deviation. The last one in this section that I want to look at is number 8. And 8 is dealing a little bit more of a word problem, but very similar. Everything's the same. So we have a mean time between eruptions of 69 minutes. Let the interval of time between the eruptions be normally distributed with a standard deviation of 27 minutes. So on this one, that one randomly selected time interval between eruptions is no longer than 82 minutes. So this is dealing with one thing. So our mean 69 and our standard deviation is 27. So we have a mean of 69 and a standard deviation of 27, and they're looking to see that will be longer than 82 minutes. So longer than 82 minutes. And we get our answer, 0.3151. Again, because that's when we were only dealing with one interval. So now we have 12 time intervals, right? So instead of our standard deviation being 27, it's going to be 27 divided by the square root of our sample size, which is 12. So this is the standard deviation that we're going to put in here. So 7.7942. Try to go maybe out to 4 decimal places on these. 7.7942. And still longer than 82 minutes. So do you think that this probability would go up or go down? And it's going down because, again, we're getting closer and closer to the mean with the larger sample size we get. So that means less and less of the population will be greater than that 82. So now we get a 0.0477. 0.0477. And so they keep doing this, but now it's going to be 21. So we have to recalculate this standard error of the mean. So as your sample size increases, the distribution should get tighter around the mean. The standard deviation gets smaller because we're dividing by a larger number as our sample size goes up, and that means there's less variation around the mean.